In this module, we are going to consider equilibrium of a rigid body. There are two kinds of equilibrium, one called stationary and the other static. Both of them need to be defined in terms of an observer in an inertial reference frame, and both of them are defined such that the object displays no linear or angular acceleration. But the difference between stationary and static equilibrium is that in static equilibrium, we also have no linear or angular velocity. Most important is that there is no angular velocity. Notice that we can always remove any linear velocity by changing to an inertial reference frame in which the object has no linear velocity. But we cannot do the same thing for angular velocity because making such a change of frame to remove the angular velocity would put us into a non-inertial reference frame. So what's really important for equilibrium problems is that we make sure that there are no net external forces and no net external torques acting on an object. In this case, the object will have no linear or angular acceleration and will be in equilibrium. A useful detail to note is that we can compute the torques about any origin. A clever choice of the origin can lead to much simpler problems. In general, the sum of all the forces and sum of all the torques lead to a total of 6 equations that need to be solved in 3 dimensions. This can lead to problems which are quite complicated. To simplify life, we're going to consider only coplanar static equilibrium. This means that we're going to limit ourselves to cases where there are no forces perpendicular to a particular plane and no torques that are in the plane. So if we consider the case where our problems are in the xy plane, then we must consider the sum of all the forces in the x direction vanishing. Those forces in the y direction must also sum up to 0. And the sum of all the torques which are in the z direction must also sum to 0. Now, with this simplification, what we wind up with is 3 equations, which mean that we are going to have problems which can have up to 3 unknowns and still be solvable. To understand this better, we want to consider an example. So consider a construction worker weighing 80 kilograms who stands at the end of a 4-meter long steel beam weighing 45 kilograms. The beam is attached to a wall and is further supported by a strut attached to the wall and to the beam at a distance of 3 meters from the wall. The strut makes an angle of 60 degrees with the wall. Find the magnitude of the compressive force exerted on the strut and the force of the beam on the wall at the point where the beam attaches to the wall. Now, to answer the question being asked, what we really want to do is to find the forces on the beam that keep it in equilibrium. Then we can use Newton's third law to figure out what the forces on the wall and the strut are based on the forces needed to keep the beam in equilibrium. To start with, what we want to do is construct a free body diagram for the beam. So we take the beam, and then we note that it is 4 meters long. Its weight will act through the center of mass of the beam, which is at 1/2 L. And we're also going to have a force acting at the far end of the beam, a mass M2, which is the mass of the worker. So we're going to have a force of gravity acting there. There's also going to be, acting at a distance d from the wall of 3 meters, a force from the strut, and that force is acting at an angle of theta, which is 60 degrees. Finally, we have a force acting at the point where the wall meets the beam, and we can break this force into 2 pieces. So the reaction force in the x direction, we can tell from the direction of the strut force that the x component of the reaction force is going to be acting to the left. And then we are also going to have a y component for this force. Now, we don't know at this point exactly which direction this is going to be. It could be up or down. We're going to assume that it is down, and if we're correct, our value for the force will be positive, but if we're wrong with our choice, then we simply will get a negative answer. To solve this problem, we start by looking at the sum of all the forces acting in the x direction. So, in the positive x direction, we have the force from the strut. The x component is Fs sine of the angle theta, and acting in the minus x direction is r sub x, and those two sum to 0. We next consider the sum of all the forces in the y direction. Again, the strut has a force acting up. Its y component is Fs cosine theta. Then acting down are the reaction force, r sub y, and the weight of the beam and the weight of the person standing on the beam. These all add to 0. And finally, we need to consider the torque acting on the beam. And in this case, let's consider the torque acting through a center of rotation at the end of the beam where it attaches to the wall. And we're also going to assume that our positive torques are those which create a rotation in the counterclockwise direction, and thus a torque which is in the positive z direction coming out of the screen. So first we have acting the torque due to the strut. It's acting at a distance d from the point of rotation, and the perpendicular component of the force in that direction is the y component, Fs cosine theta. So those we add because they're causing rotation in the counterclockwise direction. Also acting are the weight of the beam, which acts at a distance of L over 2, which is the point of the center of mass of the beam. And so then we have at L over 2 the weight of the beam, m sub 1g, acting down. And the second torque acting down is the weight of the person standing at the end of the beam, a distance L away from the point of rotation. And the force then acting perpendicular to this distance is m2g. So those all sum to 0. We can immediately solve this torque equation to find the force of the strut on the beam. Once we know this, we can plug this into the first equation to immediately tell us what the x component of the reaction force is, and then also into the second equation to get the y component of the reaction force. Plugging values into these, we find that the force in the strut is 2,679 newtons, the x component of the reaction force is 2,320 newtons, and the y component of the reaction force is 114.3 newtons. We get a positive value there, so we know that we chose the direction of R sub y correctly. And this means that to answer the full question which was asked, which is what is the force on the wall first, that turns out to be a positive 2,320 newtons in the x direction plus 114.3 newtons in the positive y direction. So pulling up and out on the wall. And then there is a compressive force on the strut of 2,679 newtons. But let's recall that we have the freedom to choose the point about which we define the torques. So in this case, let's consider the torques to be defined about an origin, which is at the location where the strut is applying its force, a distance d from the wall. In this case, when we now start defining our torques, the first positive torque is going to be given by the reaction force, Ry, acting down at a distance d from the point of rotation. We're also going to have a positive torque coming from the weight of the beam. It's acting at a distance of d minus L over 2 from the point of rotation, and the force then perpendicular to this is m1g. And then acting in the opposite direction is the weight of the person at the end of the beam, acting at a distance of L minus d from the point of rotation, and the force being m2g. So when we solve the torque equation, we can solve it immediately for the y component of the reaction force. This we can plug into the second equation to immediately give us the compressive force in the strut. And then we can use this to tell us the x component of the reaction force. So in this approach, we can again get the exact same values for the three unknown parts of the forces. And we could choose any other point we want to define the center of rotation for defining the torques. But if we do this, we're going to have a harder problem because any other choices than the two we have chosen would lead to the torque equation involving both the Ry force and the Fs force, and then we would have to solve two equations for two unknowns simultaneously, which is not hard to do, but it is harder than doing it by the two previous choices for the centers of rotation.